Hang on, I gotta record this for a second. Alright, so here's what you should know as of now in topic number 5. You should know that we are simply organizing electrons around the nucleus, and that thing is called electron configuration. Basically, you are organizing the electrons. How do you organize them? Use that. Use that on every assessment, practice sheet, I don't care. You can use it. All your assessments are open notes. You can use whatever you want on your assessments. I don't care. We also learned at the end of the last time we were together, which was Tuesday, the last time we were together, we looked at this so-called valence electrons. Scientists realized that once they established an electron configuration for any atom, the electrons that are really involved in how an atom behaves are near the end of a configuration. The end of a configuration is where you will find the number of valence electrons. And it's these electrons that determine how the atom behaves. I told you last time that these are the electrons in the highest main level. I also told you that when it comes to the sublevels that are used for valence, you only have to use S and P. And I showed you why D is never part of that. D is never part of valence because there's always some higher main level S that kind of comes over and eclipses and kind of cuts them off, you could say. Which is nice. You only have 2 to worry about. No, don't ever look for the D or the F when you're calculating the valence, which is really, really nice. And I think some of you know this. Well, if these are the only 2 sublevels involved in valence, then there can only be a maximum of 8. That's it. If you have a valence of 9, 10, or beyond, something's wrong, man. You grabbed the wrong sublevels. And I think some of you already see where the 8 comes from. S and P. An S sublevel, that sucker only holds 2 electrons as a maximum, and the P holds 6 as a maximum. Therefore 2 plus 6 is going to give you 8, and that's it. Now that took me 2 days to get to this point. It's just a lengthy process. So here's what we're going to do next. We are going to practice, review these 2 for some very select atoms off of the table. I'm going to pick very selective ones because what I show you in these practice problems, I'm going to use later on the rest of today. Okay, so I'm going to be very selective. You really need to try these and work them out. Because if you can't do these, then you're going to be in trouble as we progress in topic 5. Okay? So you betcha, get this baby out. Hey, I'm going to get mine ready. I'm going to have mine available right here. I'm going to have my table ready. Boy, I hope you have a table. Say goodbye to this. All right, I'm going to be very selective, and I want to start with, let's start with this guy right here. Now notice where he's at on the table. He's to the very, very far left. This is the guy I want to start with. Let me show you. Okay, it's good old sodium. And you know from topic 3 that that is the number of electrons outside the nucleus. So let's use sodium and his 11 electrons. So I'm going to go way over here, and I want to use sodium. He has 11 electrons. Okay, here's what I need from you. All of you should try this. I need his electron configuration. Please use your flowchart. Get the proper electron configuration for an atom of sodium with 11 electrons, and then please calculate his number of valence electrons. Okay, go. Go, 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 go. I hope you're trying this. All right, go. Okay, let's check your answer and see if it matches mine. So here's what I hope you did for sodium. We know we start here and we go to the lower left. We're always going from upper right to lower left. So I'm going to go down this line. Here's the first guy I hit, 1s2. I continue in the line, and then I hit this so-called little loopy part, and so I go around here, and now I start down this line, and the first guy I hit is a 2s2. Keep going, so I finished my so-called green line. I loop back around, and now I start down here, and this is the next guy I hit, which is a 2p6. Okay, then you just have to stop at some point and find out where you are according to your 11 electrons. And that's where you simply go back and count. And you use these numbers. Hey, there's 2 electrons. There's 2 more for a total of 4. Plus 6. Hey, I'm at 10 electrons right now. I'm almost done. I only need 1 more to get to 11. So I go back and I find out where I stopped. And then I go down and I continue, and this is the next one. Now this one holds up to 2 electrons. You don't need all of them. You don't need both electrons. You just need one of the 2 to reach your 11. So I'm going to grab 3s, but I only need 1 electron in there. 3s1. 10 plus 1 is 11. Boom. Done. Valence. Valence, I told you, all you have to do is simply scan and look for the highest main level that this atom uses. Here's a 1, there's a 2, there's a 2, there's a 3. So it looks like the highest main level for sodium is main level 3, and in there, my friends, 1 electron. Ching. That's it. Questions? Okay. Now, watch this carefully. I'm doing all this for a reason, because all this is going to come together in the second part of topic 5. So stay with me. We just did sodium way over here on the left. Well, I want to jump all the way over here to the right now, and I want to pick on neon. Find neon on your table. And you already know how many electrons we have to organize for neon. Bingo, 10, okay? I want to do the same thing. Now, I'm going to start shrinking this up. I'm not going to write electron configuration every time. So what I'm going to do is I'm just going to write EC, which stands for electron configuration. And then I will write out the whole word because it's not that long. I will write out valence, but I'm not going to write electrons. Okay, so I'm going to condense this up. We are going to look at neon. Neon has 10 electrons. Okay, all of you, quickly, give me the electron configuration for neon, and please give me his valence. Okay, go, hurry. All right, let's check your answer. Here we go. I'm going to grab my blue Okay, we got neon. He's got 10 electrons. Let's write his electron configuration. Again, my friends, start here. Go to the left. Here's the first guy you hit. After you're done with this line, yes, it loops back around. Now it picks up this one. You're now using this guy. This guy is next, 2s2. After that, continue. Hey, it loops back around. I'm now going to come over here. And 2p6 is next. And you just got to pick a point. And you got to stop and find out where you're at. I am at 2, and 2 make 4. Shoot, I'm done. 2 and 2 make 4. Plus 6, bingo, 10. Hey, that's it. That's it for him. Short and sweet. And then you would count those valence. Let's count the valence. Highest main level that neon uses, looks like I got a 2, and I got a 2, which means 2 and 6 together make 8. And I bet a lot of you just had 6. That's usually what I find when I walk around the room if we were in person. No. You have to get all of the highest main levels. So if there's 2 of them, then just get this grand total. That's it. Okay? All right. Stay. Hey, you got to stay with me the entire day. You got to watch this carefully. All right. So we've done Na. We've done neon. I want to now go back to the left side of the table. I want to grab the one right below Na. I want to do this guy next. I want to grab potassium. I want to grab his 19 electrons, and I want to get his electron configuration and his valence. Okay, so watch this. I'm going to go back to the left part of the board, and I'm going to grab potassium, and he has 19 electrons. Okay, hurry, quickly. Give me his electron configuration and whoops, a little more room would be nice. Hello. Give me the valence. Okay, this should start to go faster the more you practice writing these things out. Okay, my friends, go. Use your flowchart. Take care of potassium. Okay, let's go. Let's check. Let's see. I'm going to grab my level flowchart. Oh boy, okay, 19. Okay, this will be a little bit longer now. But hey, you guys, it's the same routine. You start here. Here's the first guy you hit. After that, I continue. I see I loop back around. I come around here. Now I hit this line. This is the next guy I hit, 2p2. Oh, sorry, 2s2. Hey, after my green line, I loop back around. Now I'm over here, and I'm going to go on my blue line. This is the next guy I hit, 2p6. After 2p6, I keep going, and this is the next one I hit in that line, a 3s2. After a 3s2, I'm out of my blue, and now it looks like I'm going to loop back around and now pick up this orange. And remember, always right to left. This one's next, 3p6. And like I said, you have to find a point to stop, and then you count. Wait, where am I? So you go back, and you go, hey, 2 and 2 make 4, plus 6 is 10. That's 12, and 12 plus 6. I'm at 18 right here. Well, that's nice. Look, I got to get to 19. I only need one more electron. Well, let's see what's next. I just did a 3p6, which is this guy right here. I need one more electron, and it has to go inside a 4s. But I don't want to use 2 electrons, because that would bring me over 19. I only want 1. Remember, you can always be less than these maximum numbers. You just can't go over those numbers. So keep that in mind. Woohoo! Look at that. Now I find my valence. I'm going to simply scan my configuration, and I'm I'm going to look. No ones and the twos and the threes. Looks like the highest main level is a 4. And in there, woohoo, 1 valence electron. Okay, what have we done? We've done Na, and then I jumped way over here and grabbed neon. Then I moved back over here and I grabbed potassium. Yep, you're right. Guess where I'm going to go now? I'm going to go way back over here to the far right, and I'm going to grab argon. Argon. Hey, what's a pirate's favorite element? Argon. Okay, that was funny. I have a million chemistry jokes. Arg. All right. So let's go. Okay, I've got more. Don't worry. Argon. 18. Would you please? And you're probably getting better at this each time you guys go. Come on, keep going. Give me the electron configuration quickly. And would you please give me his valence? Argon. Okay, I'll stop. Okay, let's take a look. So we got this for argon. Was 18, which is one just before the potassium. So then I jumped from this side of the table, which is the right, all the way back to the left. Now come on, look at this. You guys are smart. Look at this. When I start to figure out his configuration, I get 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Holy crap, this is a big one. 3d10, 4p6, and holy smokes, you better have a 5s1. Whew. It's okay, my friend. You just have to continue. You just have to continue through the flow chart, and then eventually you'll get to the end. And then you better have, did I do it right? 2 is 10, 12, 18, 20, 30, 36, 37. Okay, good. Okay, let's go back and look. Hey, how many valence? You got to scan. Just scan the list and find the highest main level that rubidium uses. And it looks like the highest main level is a main level 5. And in there, 1 electron. Good, 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 good. Okay, last one, and I'm going to wrap all of this together. So what have we done so far? We did sodium over here, and then I jumped over to neon, and then I jumped back to potassium, which is on the left side of the table. Then I jumped back to the right. Then I jumped back to the far left. Yes, we have to complete the pattern. Let's jump to the far right now, and let's take care of good old krypton. Krypton on your table, 36 electrons. Come on, you can do this. Let's go. Let's get krypton in here. His 36 electrons. Let's get his electron configuration, and then let's get his valence. And I hope you'll see the pattern that's starting to develop with these 6. Okay, hurry, go. All right, here comes my answer. If you're not done, keep going. Here comes my answer. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and a 4p6. Bingo, there's 36. Valence, scan, look, highest, main level. Okay, I've got 2 4s. I'm going to take the total. There's 2, and there's 6 total. 8. All right, right, my friends. I hope you can see the pattern now. Come on, look, you're smart. Otherwise you would not be in this kind of class. Look, 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 look. Okay, let me just flip this table over on the side. Okay, see these guys right here? I took them all from this column. The last guy was rubidium. The first guy I did was Na. No, I did not do Li, which is lithium, but if I did, you probably could predict his valence. Yeah, it's going to be 1. I didn't make you guys do cesium, which is 55, but he's in this same group. Yeah, I think you get the idea. His valence would also be 1. I did not make you do francium number 87. We don't have to. His valence would still be 1. Okay, now look what I did. I went to this side of the table, to the very far right. I grabbed neon. I calculated his valence would be 8. I then did argon. You guys did a great job on this. You found his valence to be 8. We then jumped down to krypton, which when you were done, you realized, crap, his valence is also 8. I didn't make you do xenon or radon, but if we did, you would find 8. That's the pattern, my friends, and that's why the valence can be no larger than 8 total electrons. 8 is it. And so if you look at this table, these guys are 1s, these guys are 8s, which means these guys in the middle are the area in between. All these guys have 1 valence, these guys have 2 valence, then it gets to 3 valence, 4, 5, 6, 7, and 8. There is a massive pattern with this table. 1, 8, and here's the guys in between. Now, some of you already know a little bit about neon, argon, krypton, xenon, or radon. You've heard of these. Oh yeah, we can put helium in that group too. Helium is too small to have an octet, or I'm sorry, a valence of 8. Okay, he's got a valence of 2. We'll get to him eventually, but here's the main block right here. I bet you have heard a name applied to these guys to the far right. And that name you probably heard before was noble gases. Yeah, these are noble gases. You've heard of them before. These guys on the far right are extremely stable. Extremely stable. And that's why they were classified and given the name noble. And they're gases at room temperature and pressure, so they added that word in the end. Noble means prestigious. Noble means something special. What's so special about all these guys on the far right? They all have a valence of 8. Something else you probably know about these guys on the far right, if I was to place argon on my desk, I could come back in 200 years and it would still be there unchanged. It's not going to change. These guys don't react. They're too stable. Why are they extremely stable? They have a valence of 8. Okay, now I flip it. Now I'm over here. Now I'm on the opposite end of the spectrum. Valence of 1, valence of 1, valence of 1, 1, and 1. You might not know about these, but I'll tell you about these guys. If I was to put lithium on my desk, yeah, I would probably have about 2 minutes to walk to safety. After that, it's probably going to explode. Sodium, you put that on my desk, well, I don't have 2 minutes. I probably have about a minute to get out of the way, and that thing's going to start reacting and will explode. Potassium, no. Hey, you don't have a minute. You've probably got 15 seconds to run. And obviously, if we were in person, I would show you these on my desk. I have actually burnt a hole in my ceiling showing students how reactive these little mothers are. Hey, I can't even buy that, by the way, rubidium. You put that on my desk, you're probably just going to get the lid off the container and it's going to be too late. That stuff is extremely explosive. Nope, you can kiss that goodbye. You can't even buy that. And the military owns francium, so that tells you about francium. So that's really weird. These things are extremely reactive, And these guys sit there like you and do nothing. Weird. Let's take a look at these guys that are stable and do nothing. Okay, hope you see the pattern. Okay, watch this. Let's take a look at those noble gases on the far right side of the table. Yes, they are called noble gases. Noble means there's something that's special about them. And that special is the fact that they've got 8 valence electrons. What's so special about that? They are extremely stable. They will sit on my desk and do nothing for a long, long time. Hang on, I gotta fix, somebody wants to come back in the room. Mr. Diaz. Yep, all right, let me get him back in here. Stable. Hey, these things, they don't react at all. Sit there on my desk and do nothing. Matter of fact, my friends, you probably know that these guys are so safe and don't do anything. You can put this in balloons and hand it to little kids. That's how stable these guys are on that far right. So the question becomes, okay, well, what if I have atoms that don't have a valence of 8? They need to do something. They want to do something. They all want a valence of 8 electrons. They have options. To get a valence of 8, like, let me go back to sodium real fast. Remember good old sodium number 11? 1s2, 2s2, 2p6, 3s1. Okay, look at his configuration. There. Look. Sodium would love to simply take this 1 electron and release it and lose it. Because if he loses that 1 electron, look what you have now. Now the highest main level is a 2, and in there I have 2 plus 6 is 8. So what sodium would love to do, sodium would love to lose this electron, which creates a highest main level of 2, and in there he's got 8 valence electrons, which now matches these noble gases. But when sodium does this, when sodium loses electrons, there's a price he's going to pay. Just like when you're sick and you need to take some medication, there's always some kind of side effect that goes with taking some medication. Well, there's a side effect in the atomic world when atoms lose electrons. Now, there's the opposite. There's the opposite. I didn't do this to you, but take a look at this one. Take a look at fluorine. He's right here. He's number 9. Look at fluorine. There's his configuration. 2 and 2 make 4, plus 5 is 9. Take a look. Highest main level's a 2. I see 2 electrons in here. I see 5 in here. Looks like his total is 7. Holy smokes, you guys, look. Look how close fluorine is to 8. He is so close. All he needs to do is he needs to gain 1 little electron and put that in here. Whoops, sorry. Put it in there and get this 5 up to a 6. Because now 6 plus 2 would do the 8. And that's the choice atoms have. They can either lose electrons or they can gain electrons to get this valence of 8 and basically copy what these guys have. Now I'm going to help you figure out what the atoms will do. Will they gain or will they lose? And what is this side effect that comes along with this decision to lose or gain electrons? You are going to make the second most important table of your life. Let's get rid of this. The second most important table of your life. 3 columns. Let's do this. Let's go let's go valence. If I take a look at all the possibilities that exist for atoms in terms of their valence, well, I know it ranges between 1 and 8, but 8 is stable. So I'm really looking at 1 to 7. What's going on with atoms with a valence of 1 to 7? What are their options? Let's pick on the small ones first. If an atom has a valence that ranges between 1 and 3, remember, there's only two options. Do they gain or do they lose? Do they gain or lose? Well, when they're in this range, like I just showed you for sodium, and I told you sodium would lose electrons, that's what these atoms will do. They lose all valence electrons. They lose them all. They'll chuck them all. Now, I told you, just like if you were sick and you take some medication, there's always a side effect. Here's the side effect in the atomic world. It's actually called an oxidation number. So I could say to you, ooh boy, you take that medication, you're going to get a stomach ache. Atom, if you lose electrons, you're going to get an oxidation number. It's the same kind of thing. What is this oxidation number? What is this so-called side effect? Well, I'll tell you what. If atoms lose electrons, they become positive by how many they lose. And the side effect in the atomic world is not a stomach ache, it's gaining some kind of electrical charge, positive or negative. Now, don't worry, I'll show you where this comes into play, because this is the next part of your topic 5, which carries over for the rest of the semester. We'll be looking at these forever. Here's where they come from. 4. Think about that one. Come on, you're smart. That's a bad spot to be in. Or is it a good spot? That depends. So we have atoms, we have elements that have a valence of 4. You know why 4 sucks? It's halfway between 8. So do they gain or do they lose? Well, that depends on who you're combining them with. Now that takes a couple topics later to figure out. So for now, for us, in topic 5, don't worry about it. Don't worry about it. I'll get to it later. I'll get to it later, probably in topic 7. Okay. Just leave 4s alone. Okay, your last option. Now we have these atoms, like I showed you with fluorine. Fluorine sucks. Fluorine is a very reactive element. You put him on my desk, it's over. That sucker is going to react with anything and everything it can get a hold of. Because fluorine is sitting right here at 7 valence electrons. So close to that so-called stable octet. Now it's the opposite. It's the opposite. These guys don't lose. They gain enough electrons to obtain 8 valence electrons. Now, this so-called 8 valence, they will actually use a different word. They will use octet. Again, that's going to come up later in a later topic. And some of you already know that the name for 8 is octet. That's where they get it from. Because scientists back then, they were heavily into music, and so they tried to apply music to the atomic world to see how they behave. So it's music and science coming together, which is usually a great combination. They might also throw in this, which is a stable octet. It's the same thing, just they might want to emphasize the fact, oh hey, they're stable. And yes, the valence is 8. Okay, so please just keep this in mind somewhere in your notes off to the side. Maybe it would be good. There's a price they pay. I'm telling you what, you in the atomic world, you don't do this and get away with it. You don't. You pay the price. And now the price is the opposite of this. Negative. By how many they gain. Keep this table handy. Keep it nearby. I even had some students in the past when we were in-person education where they put this on a separate piece of paper. That way they could simply pull it out and use it over and over and over again. Example. Okay, look up here. Hey, if I have an atom with a valence of 2 electrons, he fits within this range. How many will he lose? He'll lose all of them. He'll lose all 2. If he loses 2, he becomes positive by how many they lose. Well, if they lose 2, plus 2. He'll be plus 2 as his oxidation number. If I got a valence of 3, no question, easy, lose them all. He'll lose 3. If you lose 3, his side effect is having an oxidation number of plus 3. Hey, if I got a valence of 6, if I got an atom with a valence of 6, he's going to gain up to 8. So if he's at 6, he's got to get 8. Well, there's 1, 2. He's got to gain 2 electrons. If he gains 2, he becomes negative 2 for his oxidation number. A valence of 7. Well, he's already at 7. He needs to gain 1 more to get to 8. Gain 1 electron, boom, his oxidation number becomes negative 1. And then we ride this thing until the end of the semester. And let's take it in chunks. Let's just kind of chunk this thing out. Questions on this? Oh no, my cat. Oh. Go bug someone else. Okay, let's put all of topic 5 together now for one atom, and let's see where you're at. And this will show you what you should know by now in topic 5. All right, let me just pick an atom. Let's pick gallium. He's not too large. Gallium has 31 electrons. Here's what I hope you can do now using all the notes you have. Shh, cállate. Oh. You should be able now to give me the electron configuration for gallium. Second thing I hope you can do by now using your notes is his number of valence electrons. 3. I hope using your notes in that table, can you tell me if this atom would gain or lose electrons? And then number 4, which happens to be the ultimate topic of topic 5. There's too many topics and parts. Man, that almighty important oxidation number, which will carry on with us for a long time. Okay, I will stop talking. Would you please do those 4 things? All right, Kat, what do you... Okay, let's see if your answers match mine. Electron configuration using your flowchart. 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4. Oh, wait a minute, I'm over. Oh, just 1. Yeah, is that 31? 2, 4, 10, 12, 18, 20. Bingo, right there. Valence. Okay, my friends, just scan the whole thing. 2s, 3s, 4s, 3s, 4s. I got 4s. That's it. And then I grab a total. I'll take his 2 and his 1, and together I get a grand total of 3. Now, based on that table that we just constructed with the valence of 1 to 3, sucker's got to lose. Now, please, when you answer this on your assessment that's due on the 26th, don't say just lose. That doesn't work. You have to say, oh, yeah, lose, and then how many? Okay, you have to quantify the loss. If you don't quantify the loss, I'm going to mark you wrong. I have to. And then based, again, on that same table, if an atom loses electrons, it actually becomes positive by how many you lose. And so you can think of it this way. Think of it when it loses, it becomes positive by how many it loses. And usually students go, wait a minute, how can you lose and become positive? You have to remember the charge of an electron that I gave you in topic 3. Topic 3, I told you the charge of an electron is negative, and the charge of a proton is positive. Well, we haven't changed the protons. There's still 31 protons in there. You can't change that. Hey, originally there was 31 electrons. Well, you add that up, you get 0. But he tries to obtain this so-called stable octet, and so he plays a game with the electrons. But, you guys, you can't change the number of protons because that's what gallium has. He's got 31 protons. But he plays a game with his electrons to get that stable octet, and so what he does, he actually loses 3 of his electrons. If you lose 3 of those that have a negative charge, and you add it up, boom, that is why that is positive. Your assessment for topic 5, boy, we're almost ready. There's the first 4 parts of your topic. It's huge. It's a huge assessment in topic 5. All right, my friends, I'm going to let you out early. I am finished. I'll stick around if you have questions. If you don't have questions, hey, have a great day.
Have a good rest of your day.
All right, you too.
Bye.
See ya.